All right, today we're going to dive into one of the first and honestly one of the coolest algorithms that showed the world that quantum computers aren't just a little bit faster, they're playing a totally different sport. We're talking about the Deutsch-Jozsa algorithm. So let me set up a little puzzle for you. Imagine you have this black box, right? It's a function. You can feed it an input and it'll spit out an output. But you have no idea what the code is inside. Now you're given a promise. The function is one of two types. It's either constant, meaning it gives you the exact same output no matter what you put in, or it's balanced, meaning exactly half the inputs give you one answer and the other half give you another. The question is, how many times do you need to check the box to know for sure which type it is? Well, if you use a regular classical computer, you might have to check thousands, even millions of times to be absolutely sure. But a quantum computer? Get this, it nails it in one go, a single try. That is the insane difference in power we are going to unpack right now. Okay, so first things first, let's get really clear about the problem we're trying to solve. It all boils down to figuring out the secret identity of one of these two functions. In the quantum world, we call this mysterious black box an oracle. You can think of it like a program you're allowed to run, but you are absolutely not allowed to look at the source code. You can ask it questions, but you can't peek behind the curtain. And we know for a fact that this oracle is one of two things. It's either a constant function, super simple. Whatever you put in, you always get the same value out, like always a 0 or always a 1. Or it's a balanced function, which is split perfectly down the middle. Exactly half the inputs will give you a 0, and the other half will give you a 1. Our entire mission is just to tell these two apart. Now, to really appreciate just how slick the quantum solution is, we have to understand why this is such a headache for a normal computer. So a classical computer just has to brute force it, right? It asks, hey, what's the output for this number? It gets back a 0. Okay. Then it tries another number. It gets back a 1. Bam, game over. Different outputs means it has to be balanced. Easy. But what happens if it gets a 0 again? And on the next try, another 0. You see the problem? You can never be 100% sure it's constant. You just have to keep checking, hoping you'll eventually see a different number. And this is where it gets really ugly. In the worst-case scenario, for a function that takes n bits, you might have to make this many queries to be absolutely certain. That number, it grows exponentially. It gets impossibly big, ridiculously fast. We're talking about a problem that can go from trivial to taking longer than the age of the universe to solve. It's a hard wall that classical computers just run straight into. So enough of that classical slogging. Let's jump into the quantum realm and see how it builds a solution that is just, well, beautiful. Our first secret weapon, of course, is superposition. You know, superposition is that mind-bending quantum property where a qubit can be a 0 and a 1 at the exact same time. Well, if you string a few of these qubits together, you can create a state that represents every single possible input to our function, all existing simultaneously. This is the heart of so-called quantum parallelism, the ability to get ready to check everything in one single operation. And the specific magic wand we wave to do this is a quantum gate called the Walsh-Hadamard transform. I love this analogy. Think of it like a prism. You know how a prism takes one beam of white light and splits it into a whole rainbow? Well, the Hadamard transform does that to our qubits. We start with a simple state of all zeros. We apply the transform and poof, we now have a perfect, balanced superposition of every possible state. We are now ready to query the oracle about everything at once. Okay, so we're holding all possible inputs at once in our superposition. But how do we actually get an answer from that? We can't just look at it or it will all collapse. And this is where the pure genius of this algorithm really shines. See, the big twist is that we're not actually going to ask the oracle for an output. If we did that, the whole superposition would just collapse to one random answer and we'd be right back where we started, having learned almost nothing. No. Instead, we do something far more clever. We use the oracle to encode its global property, is it constant or balanced, directly onto our quantum state. It does this using a property called phase. You could imagine each state in our superposition as a little wave. The function doesn't change the wave's amplitude, but it can give it a little nudge. That nudge, that shift in the wave, is the phase, and that is where the answer is going to be hiding. This beautiful little mechanism is called phase kickback. The function essentially kicks back information about its output into the phase of our input qubits. So if the function's output is a 1 for a particular input, it flips the phase of that component in our superposition. If the output is a 0, it leaves it alone. This creates a hidden pattern of these phase shifts across the entire system, a pattern that perfectly reflects whether the function is constant or balanced. So now the answer is encoded in the phase of our system. It's there, but it's hidden. We just need one last step to make that secret information pop out so we can read it. So what do? We take our prism, that Walsh-Hadamard transform, and we run it again, essentially in reverse, to bring everything back together. And this is the payoff. If the function was constant, then every component got the exact same phase shift. They're all in perfect sync. So when we bring them back together, they all add up perfectly. That's constructive interference. All of that energy is focused on one single outcome, the all-zero state. When we measure, we are 100% guaranteed to get all zeros. It's a dead certainty. But, and this is so cool, if the function was balanced, the exact opposite happens. Half the phases were flipped, half weren't. They are perfectly out of sync. So when we run the transform again, they completely cancel each other out for that all-zero state. That's destructive interference. The probability of us measuring all zeros becomes exactly 0. It's impossible. So if we measure anything else, and we're guaranteed to, we know with 100% certainty the function had to be balanced. And that's it. We've figured out the global property of the entire function with a single call to the oracle, a single query. Compare that to the classical method that could take longer than the lifetime of the universe. This is a perfect textbook demonstration of quantum advantage. Now look, the Deutsch-Jozsa algorithm isn't something you're going to use in your daily life, but its importance cannot be overstated. It was one of the first major signposts that proved that quantum computing wasn't just a quirky theory. It showed that by thinking differently, by using superposition and phase, we can attack problems in a fundamentally new way. And it really makes you wonder, what other impossible problems, what other exponential walls are just waiting to be knocked down by a quantum computer?